All right, so this is section 1.4, and in the previous section we introduced matrices. We talked about some notation, some operations you could perform on matrices. Spent a good chunk of time talking about matrix multiplication and different ways of representing matrix multiplication. Our focus here in section 1.4 is kind of two parts. One, you can tell from the title, we're looking at inverses, which will come up a little bit later, and then we're going to talk about some algebraic properties of matrices. In fact, we're going to start with that. So this first theorem it looks huge. It's got several parts to it, 13 parts if you count them. We're saying here that we're going to assume that matrices A and B, or A, B, and C, are matrices that have dimensions that allow for the operations to be performed, the operations that are showing up here. The scalars, lowercase a, b, any lowercase letters, those are going to be assumed to be scalars. These are a bunch of laws of arithmetic for matrices that hold that can be really, really useful. So, for example, A, we have that the sum of any two matrices is commutative. A plus B is equal to B plus A. Just like with real numbers, x plus y, if x and y are real numbers, would be equal to y plus x. We call it the commutative property or commutative law. Associativity, if you're adding three or more matrices, how you group those sums won't change the end result. So if I add B plus C first and then add A, or if I add A plus B first and then add C, I get the same thing, associative law. Matrix multiplication has the associative law as well. This one is very, very cumbersome to prove, but it is in fact true. And then several other properties, distributive properties. So matrix multiplication distributes over addition, whether you're multiplying into the set of parentheses from the left or from the right. Same thing for subtraction. Scalar multiplication follows distributive laws as well. And we end up, I'll have you look through these on your own, but these are all really important properties that we can utilize when working with matrices and doing arithmetic on them. So it's far, far too much to try and prove all of these properties. But I am going to walk you through the proof of one of them because the process of proving a matrix property like this is probably an unfamiliar one. And I actually put a document on Canvas that talks about how to prove matrix properties like this. So the important thing to notice is that every single one of these properties is making a statement about matrix equality. It's saying the matrix on the left side is equal to the matrix on the right side. And we talked about in section 1.3 what it means for two matrices to be equal to each other. It means that the matrices on both sides have the same dimensions, and it also means that corresponding entries are equal to each other. So that means our proofs are also going to have two parts. There's going to be a statement or a justification for the same sizes on either side of the equal sign. And there's going to be a proof that shows that the ijth entry, which is just some arbitrary entry in one of the matrices, is equal to the ijth entry, the corresponding entry, in the other matrix. Because I and j aren't specified, those are arbitrary, that would imply that all entries in one matrix are equal to their corresponding entries in the other. So the one we're going to prove here is j, which says that if you have a plus b, where these are scalars, move that down, the sum of a plus b, the scalars, times a single matrix c, you can distribute that matrix over the scalars, and it becomes ac plus bc. Okay? Now, oftentimes when people want to prove matrix properties, they want to draw these big matrices, and they want to do all the operations that way. And you can prove matrix properties that way, but it's really, really cumbersome, really messy. And oftentimes when I've seen people do that, they aren't careful. Let me just give you an example. If I wanted to prove this property, and I wanted to actually draw, write out big matrices, it wouldn't suffice to pick like a 2x2 matrix for C and just call the entries like A, B, C, D or something like that. And the reason for that is because this should be true for matrices of any size for which these operations are compatible. Simply proving this for a 2x2 matrix doesn't actually prove the property in the general case. So we need to be more abstract in how we approach our proofs. All right, enough of that. So let's go ahead and go through this one. Let C be an m by n matrix, and let A and B be scalars. Now, you have to, this is kind of the more wordy part. So we have to talk about what different operations do to the dimensions of a matrix. Scalar multiplication, as we know, doesn't change the dimensions of a matrix. So these three matrices, A times C, B times C, and then A plus B times C, all three of these would also be m by n matrices, since all of them come from doing scalar multiplication on the matrix C. In addition to that, if you add two m by n matrices, the result is also an m by n matrix. We know that from how we defined addition. So what that tells me is that AC plus BC is also an m by matrix. Therefore, AC plus BC and A plus B times C are both m by n, so they have the same dimensions. That shows that the matrix on this side has the same dimensions as the matrix on that side. We need that explanation before we launch into this other part of the proof. Okay, now in order to prove that the ijth entry of the matrix on the left side of our property is equal to the ijth entry on the matrix of the right side, or of the matrix on the right side, we need to use the definitions of these different properties or these different arithmetic operations. So here's the matrix that's showing up on the left side, A plus B times C. And the larger parentheses indicate that we're going to single out the one of the entries of that matrix, the ijth one, to keep things general. What is the ijth entry? Well, according to how we multiply matrices by scalars, we would start by looking at the ijth entry of the matrix C, which looks like this, and we would multiply it by the scalar A plus B. That's what scalar multiplication is. So it looks like I just pulled this set of parentheses out of the larger set of parentheses, but that's really using the definition of scalar multiplication that we came up in 1.3. Now, at this point, because this thing represents the entry in the ijth position for matrix C, that's just a real number, as is this. So I'm looking at a real number times a real number now. That thing is not a matrix. C is a matrix, but when I put these parentheses around it with the ij here, I'm talking about an entry in that matrix. So this is actually a scalar times a scalar, and at this point we can use properties that we already know exist for real numbers. The real numbers have the distributive property, so that ijth entry of C will distribute over this sum of scalars, giving me A times the ijth entry of C plus B times the ijth entry of C. Each of these corresponds to each of these. But and again, I'm using the definition of scalar multiplication. So A times the ijth entry of C is the ijth entry of AC. Similar here. And then finally, going from this step to this step is just using the definition of matrix addition. So that shows that the ijth entry of the matrix on the left side of my property is equal to the ijth entry of the matrix on my right-hand side. And together with this justification up here, we've shown that this property is true. It seems like overkill going through all this, but that's how mathematical proof feels when you're first getting used to it. It feels like you're taking what might feel like a relatively simple concept and going way overboard in the amount of detail for proving it. And that's for very good reasons. We're not going to go into that right now, but just kind of get a sense of what this proof felt like, and that's what a lot of your proofs for matrices in particular are going to look like. Anyways, moving on. Certain matrices show up so often that we give them special names. So anytime we're dealing with a matrix whose entries are all zero, we simply call that a zero matrix. These are really useful matrices in some stuff that we're going to do later. The zero matrix is often denoted simply by 0, and actually normally this would be bolded, so think of it as like a bold 0. If we need to specify the dimensions of the matrix, which we oftentimes don't in the notation, we can do that by writing an m by n in the subscript here. But these are all examples of 0 matrices. Okay. All right. So 0 matrices have a lot of properties that make them function very similarly to the number 0 in the real numbers. Those are all listed here. So if A is any matrix, and we add the 0 matrix of the same size to A, in either order, A plus 0 or 0 plus A, we just get A. Same thing with real numbers. 0 added to a real number doesn't change that real number. And this is very easy to see, why that would be the case. We have these other properties as well. A minus 0 is A. A minus A is equal to 0. If I multiply the 0 matrix times the matrix A, as long as the dimensions of each matrix allow for that multiplication, I get a 0 matrix as a result. And then here, we're actually going to prove this one. If I multiply a scalar times a matrix and the result is 0, then that would imply that either the scalar was the real number 0 or A was the 0 matrix, or a 0 matrix, depending on size. So this is like the zero product property that we use in algebra for solving quadratic equations and things like that. I'm going to prove this one because this is actually a useful property that we're going to need in a couple of proofs later on. So what we're going to do is first notice that this is an if-then statement. Anytime you're proving an if-then statement, which is the majority of the proofs that we have to do, you start by assuming the condition in the if statement. We're going to assume or suppose that CA is equal to 0. Okay? Now here I say either C is equal to 0 or C is not equal to 0, which, because C is a scalar, that's a simple fact. It's either 0 or it's not 0. It's got to be one or the other, right? Now if C is equal to 0, then we've established what we're trying to prove. We're trying to show that either C is 0 or A is equal to the 0 matrix, or both, but if C is equal to 0, then we're done. There's nothing to prove. So it's more interesting to suppose that C is not equal to 0. Under this assumption, in order to prove what I'm trying to prove, I have to show that our matrix A is a 0 matrix. So to do that, I'm going to proceed with a proof by contradiction. So I'm going to assume the negation, or the opposite of what it is I'm trying to prove. I'm going to assume that A is not a 0 matrix. The only way that a matrix cannot be a 0 matrix is if it has at least one non-zero entry. So I'm going to say that the ijth entry, we'll say we're going to say that the ijth entry of A is non-zero. Now let's look at the scalar multiplication here. So if I want to find the ijth entry of the matrix C times A, well, we know that that we can find that ijth entry by multiplying C to the ijth entry of A. But we assumed that C is not equal to 0, and we also assumed that the ijth entry is non-zero. So this is a product of two non-zero numbers, which would have to be non-zero as well. This is a contradiction because, again, we assumed that the matrix C times A, is a 0 matrix, which means all of its entries should be 0. So this being a contradiction means that our assumption here had to have been false. Therefore, A is equal to 0, and that wraps up that proof. Okay? All right. So from here, I want to look at some properties that matrices don't satisfy. And these are actually a little bit more interesting in my mind. So we have a lot of familiar properties from the real numbers that carry over to matrices that we just looked at. Matrix addition is commutative, it's associative, matrix multiplication is associative, we have the distributive property, all of those things. However, some very basic properties of certain operations with real numbers do not carry over to the case of matrices. We've talked about the fact that matrix multiplication is not commutative already. But the case that we talked about back in section 1.3 was a case where the matrix A times the matrix B was defined, and we found that product, but reversing the order of that multiplication was undefined. I want to look at a case where multiplication is defined in both directions. So A, B. What is A, B? 1, 0, 4, negative 2. That's A. Times matrix B. 2, 1, negative 2, 0. Okay? It's a 2 by 2 times a 2 by 2, which will result in another 2 by 2. I'm going to have 2 times 1 plus 0. That's 2. 1 times 1 plus 0. That's 1. 2 times 4 plus negative 2 times 2. That's going to be 8 plus 4, or 12. And then 1 times 4 plus 0. That's going to be 4. Okay, so this is AB. If I do BA, I'm reversing the order of my multiplication. 2, 1, negative 2, 0. times 1, 0, 4, negative 2. What's this? So starting with the first entry, 1 times 2 is 2, 4 times 1 is 4, 2 plus 4 is 6. I don't need to go any further. Already I can see that these are not equal to each other because the first entry in each matrix doesn't match. No point in going any further if the only point was to show that matrix multiplication is not commutative. Okay, so AB is not equal to BA. Let's move on to this example. This is an interesting one. So over here, in this property that we just proved, this is kind of like a version of the zero product property like we had said. If you have a scalar times a matrix and the product is equal to 0, then either the scalar was equal to 0 or the matrix was equal to 0. Interestingly enough, that zero product property does not hold in the case of matrix multiplication. So here's what I mean by that. Let's take these two matrices. 1, 0, 0, 0, 0, 0, 4, 5. Neither of these are a zero matrix, right? Neither of them is the matrix 0 because both of them have non-zero entries. However, if I multiply those, AB 1, 0, 0, 0, 0, 0, 4, 5, and you can confirm this by doing the multiplication yourself, we get the 2 by 2 zero matrix. 2 by 2, right? So what that means is that even though I had a product of two non-zero matrices, it was possible for the product to come out to be the zero matrix. That means we can't use certain solution methods that we would have gotten from algebra. If I have two matrices and I set them equal to 0, I don't get to say that one or the other is equal to 0. Okay? Now that actually leads to another kind of interesting I'm sorry, actually, I wanted to mention some terminology here. When you get this, when you get a product of two matrices that's equal to 0, then we call these matrices zero divisors. We don't really deal much with zero divisors in this class, but if you are majoring in math, you'll go on to take a course in abstract algebra, most likely, depending on where you go to college after this. The course will include a topic called ring theory, and in ring theory, zero divisors are a major topic. So this is kind of an example of that. All right. Now the fact that zero divisors exist in sets of matrices implies this next property, and we're not going to show the connection between the two, but we are going to go through an example. So I have three matrices here, and I'm going to compute AB. A times B. That's 0, 1, 0, 2 times 1, 1, 3, 4. Okay, so multiplying that, so it's going to be 0 plus 3, which is 3. I'm going to have 0 plus 6, so that's 6. 0 plus 4, that's 4, and then 0 plus 8. Okay, so AB is the matrix 3, 4, 6, 8. Now I'm going to do AC. Okay, so again, 0, 1, 0, 2. C is equal to 2, 5, 3, 4. Okay, so again, 2 times 0, 3 times 1, that's 3. 2 times 0, 3 times 2, that's 6. 5 times 0, 4 times 1, that's 4. And then 5 times 0, 4 times 2, that's 8. Notice I got the same answer. Same thing, right? So what that means is AB is equal to AC, which I have written right here. Now, if these were real numbers, notice that none of these are the zero matrix. So none of them is like the number 0, where it's not treated like the number 0. If these were real numbers and A is non-zero, then I should be able to divide both sides of this equation by A and show that B is equal to C, right? So in other words, normally AB being equal to AC, as long as A is non-zero, should imply that B equals C. That's not true here. Even though AB is equal to AC, the matrices B and C are completely different. So that's what we would call the cancellation property. It's like canceling A from both sides. We don't actually get to do that with matrices. And it kind of goes to show that matrices don't have a valid division operation. If they did, I should be able to divide both sides by A and get that B equals C. We can multiply matrices, but we don't have any way of dividing them. Okay, so that's going to be it for this video. We'll move on and start talking about identities and inverse matrices, starting with the next one.